All right, so we had a couple examples we didn't go through in class just because I was hurting your brains enough that you guys were ready for a little bit of a break, which is totally understandable. So these are the equations that are the examples that I had prepared for you. This one, I like this one because I'm going to use slightly different notation, but still use the same derivative method. Also, I have a t in here instead of an x. Just truthfully, a lot of times when you're doing math and science, your independent variable is time, so it makes sense for us to swap in t for x pretty frequently through these problems, because that's usually the variable that is the x. So in this case, instead of using my f of x notation, I'm going to call this dy dt, because it's a way, and I didn't specify this in class, when I use this notation, I'm saying the derivative of my equation y with respect to my variable t. So it is a different notation. It means the same thing. I'm not going to stress necessarily the differences between them at this point, but I would read it as derivative of y with respect to t. So when I take the derivative of this, I'm going to have the limit. Since I'm using t's instead of x's, I'm going to have delta t is the thing approaching 0. And remember, we're going to plug in our t plus delta t anywhere there's a t in the function. That's my f of t notation. And then I'm going to subtract my f of t, or I should say the first one, let's write that out, was f of t plus delta t, and this one is my f of t. And all of that over delta t. And you did problems like this in your homeworks in the last section. I understand that your brains would probably be hurting, and trying to remember exactly how this works out is where the struggle is going to lie. So that's why I did want to make sure I reviewed this before you did your homework. In a problem like this, I see fractions inside fractions. I want to simplify that. The best thing to do is going to be combine the two on top, but they have different denominators, so legally you cannot combine them until they have the same denominator. So here we're going to have 2 over t plus delta t, and I can multiply it by a special form of the number 1. Then I have 2 over t. I multiply it by a special form of the number 1. And I put those together. So I have on top, here's a hint for you too, in math, and this is going to be especially true in this class, but from this point on, always simplify numerators, never simplify denominators. So you're going to see, I'm going to go ahead and multiply through on the top, 2t minus 2 delta t. I'm going to distribute, and of course my negative gets attached to this negative 2 on the back half. But on the bottom here, I am not going to distribute that. That is very much on purpose. If I need to distribute later, I'll distribute later, but I'm not going to worry about it right now. Alright, so I look for things to simplify. I can see something right here that will cancel out. And I'm left with negative 2 delta t over t times t plus delta t over delta t. At this point, you've got to think about my little sister. Give her some legs. And then remember that I, as the oldest, do not get flipped. T plus delta t, but my little sister, the second thing, she gets flipped upside down. Look for opportunities to simplify, and here I see a delta t on top and a delta t on bottom, and I'm going to get the limit as delta t approaches 0 of at this point multiply straight across, negative 2 over t times t plus delta t. And I can now plug in delta t equals 0. This piece will go away. And I'm left with negative 2 over t times t, or t squared. So in other words, the derivative of my function y with respect to t is negative 2 over t squared. One more problem. This one's a little more unique, so I did want to make sure I included it in our examples. And by the way, I did get these from the book. If you look in the section, these problems are worked out for you. I'm doing it just in greater detail than they did. But I picked problems that are examples that your textbook did work for you as well. Here, on this absolute value, we're going to have to do things a little differently, because our absolute value function, if you think about the graph and the slope of it, it's going to be easiest to refer back to that. So let's say that I want to find the slope, which in other words is the derivative of this function at x equals 2. There's something here that you need to know that I had not covered in the lesson. If you graph this function, it looks like this. And we have something interesting happening at the point where we want to find the slope. Now, if I want to find the slope anywhere else, I could say that for all the x's that are smaller than 2, my slope is negative 1. Just because I can see the slope triangle that's created, over 1, down 1, over 1, down 1. It's the slope in front of here. If I want to look at any of the slopes that are after x equals 2, I'm going to get a slope of positive 1. And again, up 1 over 1, up 1 over 1. But here at 2, that's something that's worth talking about. If I were to find my derivative, I apologize, you can probably hear my husband's call in the background. He's at work too. My derivative on this side is the slope, so my derivative is negative 1. At this point, my derivative is positive 1, but we have to use that idea of our one-sided limits versus our total limits. Here's a limit as x approaches 2 from the negative side. I'm going to just say f of x. Actually, it wouldn't be of f of x. It would be of the slope. The limit of my slope of my secant line would be equal to negative 1. Here, the limit of the slope of my secant line coming from the other direction is the derivative. It is 1. Your limit, therefore, of x as x approaches 2 does not exist, because we talked about last week or week before, probably week before, that when your one-sided limits do not equal each other, the limit at that point cannot exist. They have to be coming to the same number. And in this case, the slopes themselves, I've got different slopes on the different sides. Over 1, down 1, up 1, over 1. Those different slopes mean that at this point, the limit of the secant line does not exist. What that means, using our rules from this lesson, this means that the derivative of x minus 2 of y equals x minus 2 at x equals 2 does not exist. It does exist everywhere else, because anywhere you can find the slope, that's going to be possible. But here at this one point on this one graph, even though the point existed, The derivative itself doesn't. And this is going to lead to an important rule that's going to come up several times. I gave you several homework problems. I think it was like 4 or 5 problems that use this concept. That anywhere there's what we call a sharp point. At sharp points, derivatives are non-existent. So if I had a function that came to any sort of point, and let's just call this a generic C value. Here I would say that the derivative at C does not exist. So I want you to watch in your homework for when they're asking you for derivatives. If the derivative is being asked, if you're trying to find the slope or the derivative at a very specific point. If it's not at a specific point, then you can do a process, even like up here, to say, well, here it is for one set of values, here it is for another. Those still exist. But if you're being asked to find it for a sharp point, if you see that it comes to any sort of sharp point at all from the visual, that limit, that derivative does not exist. And again, even on this example where I've got curves, I should see here, on this side I've got a positive slope. On this side I've got a negative slope. Obviously a positive number cannot equal a negative number, so therefore we have one-sided limits. Therefore the overall limit cannot exist. So watch for those. Let me know if you have any questions. Those were the last 2 examples that I had for you that I wanted to go through. The homework is due on Thursday, but you have until Friday at midnight to get it into me. So if you have any questions, you've got that long to get to me. And of course, remember, I've got office hours. You can bring your questions to me then.